Hey everyone, welcome to this explainer. Today, we're taking on Chapter 1 of ninth grade math, and my goal here is to completely demystify these seemingly abstract math problems. We aren't just going to sit here and memorize formulas. We're actually going to walk step by step through 10 specific mathematical solutions from exercises 1.1 and 1.2. We'll be focusing heavily on number lines, real number properties, and operations with radicals and exponents. By the end of this session, you're going to see these concepts not as intimidating random symbols, but as logical, completely predictable tools.
Okay, let's dive right into this. Here's our roadmap for today. First up, the visual foundation. Second, the rules of the game. And third, power-ups, radicals and exponents.
Part 1, the visual foundation. Before we even touch abstract letters and formulas, we really need to ground our numbers in physical, visual space.
And this brilliantly illustrates exactly what I mean. Mathematics is heavily spatial, and seeing where a number actually lives helps us understand its true value. Notice how different types of real numbers, whether they're fractions, terminating decimals, recurring decimals, or even irrational numbers like the square root of 2 or negative pi, can all be plotted right on a continuous number line. Everything has its own specific home address.
So, let's tackle our first problem together, kind of like true mathematicians encountering a brand new puzzle. Exercise 1.1, question 1i, asks us to represent the fraction 3/4 on the number line. The think aloud question we really have to ask ourselves here is, where exactly does a fraction live between whole integers?
Let's walk through the spatial logic step by step. Step 1, well, 3/4 is positive and it's less than 1, so it lives strictly between 0 and 1. Step 2, look at the denominator, which is 4. That tells us to slice the space between 0 and 1 into 4 perfectly equal segments. Step 3, the numerator is 3, so we literally just count 1, 2, 3 segments to the right of 0, drop our point, and boom, perfectly placed. Honestly, it's incredibly satisfying when you realize a fraction is really just a simple set of physical directions.
Let's shift gears a bit for our second problem. Exercise 1.1, question 3i, asks us to represent the inequality x is less than 0. Now we're shifting from plotting a single solitary point to plotting an entire inequality. So I've got to ask you, how in the world do we draw an infinite set of numbers? Here are the steps to do exactly that. First, we locate our boundary line, which is the 0 origin point. Second, and this is absolutely vital, we use a hollow circle at 0. Why? Because the inequality is strictly less than. 0 itself is not included. Finally, step 3, we shade the entire line to the left of 0 to capture every single negative value, stretching all the way down to negative infinity. That underlying principle of the hollow circle versus a solid fill dot, it's a tiny visual detail, but it completely changes the mathematical meaning of your answer.
Part 2, the rules of the game. Because algebra is essentially a giant game, and we are about to learn the legal moves we're allowed to make. You see, algebra isn't just arbitrary calculations, it's a logical board game. Let's play detective for a minute. For exercise 1.1, questions 2i and 4i, our job isn't actually to solve for x. No, our job is to spot the hidden algebraic law in action and identify the exact mathematical property that justifies these statements. For question 2i, we have 1 multiplied by y minus 2 equals y minus 2. So the crucial point is that multiplying any real number or expression by 1 changes absolutely nothing. That right there is the multiplicative identity property. Then for question 4i, we have 9x equals 9x. It seems super obvious, right? But mathematically, stating that a value always exactly equals itself is specifically called the reflexive property of equality. Recognizing these properties is what prevents us from breaking the rules later on.
Part 3, power-ups. Let's talk about radicals and exponents. I actually like to think of the laws of radicals and exponents as video game power-ups or cheat codes that help us clean up scary-looking math expressions. Let's anchor ourselves with this foundational definition. The product rule for radicals states that if you have two radicals with the exact same index, you can combine them by simply multiplying the numbers underneath the radical sign together. Now, what's really interesting about this rule is how it acts as a massive mathematical shortcut. Instead of calculating two messy roots separately, you just fuse them together.
Let's put this power up to the test with problems 5 and 6. From exercise 1.2, we have question 1I and question 1.4. We're going to look at these side by side to really demonstrate how this product rule applies universally, totally regardless of the specific numbers hiding under the root.
Just check out this transformation. In question 1I, the square root of 6 times the square root of 6 fuses into the square root of 36. And what is the square root of 36? It perfectly collapses into a clean, simple integer, 6. It's so elegant when it works out like that. Meanwhile, in question 1IV, the square root of 10 times the square root of 11 fuses into the square root of 110. Now, it doesn't simplify into a whole number like the first one, but it's still way cleaner as a single radical. Moving right along to problem 7. Here's exercise 1.2, question 1 We need to simplify the fourth root of 4 multiplied by the fourth root of 8. The think aloud question we have to pause and ask here is, what happens when our radical has an index of 4, instead of being a standard invisible square root?
Well, the beautiful truth is, the rule doesn't change at all just because the index number got bigger. Step 1, we just verify both radicals share that exact same index of 4, and they do. Step 2, we combine the radicands, the 4 and the 8, under one massive fourth root. Step 3, we multiply them out. 4 times 8 is 32, so our final perfectly simplified answer is just the fourth root of 32.
Let's move on and see how this builds. For problem 8, exercise 1.2, question 133, we're throwing a variable into the mix. We need to simplify the fourth root of x multiplied by the fourth root of x cubed. What exactly happens when we mix our radical power up with letters?
We followed the exact same logic. Step 1. Combine them under a single index 4 radical, giving us the fourth root of x times x cubed. Step 2. Remember your exponent laws. That solitary x has a hidden exponent of 1. When we multiply, we add the exponents. 1 plus 3 is 4, giving us the fourth root of x to the power of 4. And step 3, okay, this is a massive micro-celebration moment. The fourth root and the exponent of 4 completely cancel each other out. That entire messy combination magically evaporates into a single, beautiful letter, x.
Finally, let's look at our last two problems for today. Exercise 1.2, questions 2I and 2II. Here, we're being challenged to reverse our thinking entirely. We are given fractional exponents, and we need to convert them backward into physical radical signs.
Look really closely at the mathematical scaffolding here. The denominator of the fractional exponent always becomes your radical's index, and the numerator becomes the final power you apply. For question 2.2, 29 to the 1/2 power just becomes the square root of 29. Simple enough. But question 2I is amazing. 216 to the 2/3 power. The denominator 3 means we take the cube root of 216, which is 6. Then the numerator 2 means we square that 6, and 6 squared equals 36. It is just so cool how these numbers unpack perfectly when you follow the rules. Look at what you've just accomplished. You've mastered 10 core problems across visual number lines, algebraic properties, and complex radical and exponential operations. Just remember this. Mastering these fundamental rules of real numbers and exponents doesn't just solve tonight's homework. It unlocks the entire universe of high school algebra. You now have the cheat codes. So what abstract math problem are you going to conquer next? Thanks for learning with me on this explainer, and I'll see you next time.